Good afternoon, everyone, and welcome. Out of Frame is a student-run ship-shifting publication that was born during the pandemic. It exists as the edge of architectural education between institution and autonomy, practice and reflection, spatial politics and lived experience. This year, our theme is Gap Filler, which explores the divide between architects and the practical knowledge of engineers, fabricators, and makers. Too often in school, we only encounter materials through renders and drawings without fully understanding the labor, precision, and expertise that brings them into being. With that in mind, it's a real pleasure to introduce today's guest from Quarra Stone. Alex Marshall, Vice President at Quarra and MIT and Mark alum. Brian Smith, Director of QLab, Design Engineers Sam Nguyen and Leighton Nguyen. Founded in 1989 with just 6 craftsmen, Quarra has grown into one of the leading architectural stone fabricators. Based in Madison, Wisconsin, their work bridges centuries-old craftsmanship with cutting-edge technology, from hand carving to 3D scanning to robotic milling and digital modeling. Quarra not only preserves the ancient legacy of stone, but also redefined its role in and shaping today's built environment. Please join me in welcoming our guest from Quarra Stone.
So thank you very much for having us here today at MIT. We're very excited to give this talk, and thank you for the introductions. We were going to do the introductions, but maybe we'll skip, or do you want me to pass the computer real quick? I'll pass the computer. My name is Alex Marshall. I'm the Vice President of Design and Manufacturing at Quarra Stone Company. I studied architecture at MIT, as Cheng said. So very excited to be back giving a talk about what I've been up to for the last 10 years here at Quarra. Before I joined Quarra 10 years ago, I worked briefly for Howler & Yoon in Boston for about 3 years, and gained my stamp as an architect, and then moved on to the industry side of things. I'll pass the computer to Brian real quick.
Hey, I'm Brian Smith. My background is in architecture. I have an undergrad from UNC Charlotte, and then a master's in computational design from Carnegie Mellon. I've been the technical director the last few years of our QLab team. I've been here for 10 years now.
Oh, I'm Sam Nguyen. My undergrad is also in architect. I study my master in UMich, and then I've been in Quarra for 6 years, and now I'm a senior design engineer.
Hello, my name is Leighton Nguyen. I have an undergraduate degree in architecture from Clemson, a graduate degree in Master of Science in Design of Robotics and Autonomous Systems, super long name, from UPenn, and I've been here for 3 years as a design engineer.
Okay, so we're just 4 of us today, but we are about 80 at Quarra Stone Company. We're made up of an incredible team of architects, designers, engineers, makers, thinkers, machinists, master stone carvers, you name it. It's really an incredible place. And I think, what brings us all together here at Quarra is that we love to make things. And I think that's what we're going to try to do today, is show you all how we make what we make. I'll start with a brief preface. At Quarra, we make remarkable things: architecture, sculpture, even hybrids of the two, all hewn from the oldest, most enduring material on Earth. Stone has served humanity for over 1 million years, shaped into tools, monuments, and structures. It's the hardest material to master, unforgiving yet eternal, formed before life itself and preserved beyond it. In our factory, digital precision meets handcraft. We're often asked to make the impossible from a material that resists alteration. Megalithic, heavy, abrasive, weak in tension, yet immensely strong in compression. Stone's elegance, its color, pattern, and texture, an amalgam of geologic time, emerges only through patient extraction and careful reduction. Stone is the original building material. Today, we'll pull back the curtain to expose what happens on our factory floor, where we test the limits that have defined art, architecture, and making since the beginning of the Paleolithic. So just to give you a brief kind of structure of what we're going to present, I'm going to briefly run through our production capacity in our new factory that we've built recently here at Quarra. And then I'll talk a little bit about where we get our raw material from. And then we'll go through 6 projects and give you kind of a behind the curtain look at how we make the things we make. Some of these projects may have been published in the world and you may have seen them before. I can assure you that most of the imagery that we'll show today probably hasn't seen the light of day. So I think it'll be kind of exciting to show some of our behind the curtain process. And we hope that we can influence people to challenge us more in the future. So a little bit about our factory. So a couple years ago, we had a design competition. We ended up hiring Snowhetta to design our new facility in Sun Prairie, Wisconsin. It's a 66,000 square foot facility, which is a rendering of the front of it. But we've recently completed phase one, which is getting the core and shell built and moving into the factory. And we're underway with the interior fit out of the building. Just to kind of go through our capacities here, we do everything from raw material procurement direct from quarries as raw blocks. We have all of our own slabbing capabilities in-house. Several different types of saws, but the hallmark of our production is really our 5-axis machining capabilities and our robotic machining capabilities. And then in addition to that, our handwork. So I'll just kind of flip through. Here's some of our 5-axis machining centers. This is a Breton CNC machine, very large work envelope. It fits a 2.2 meter tall object on a work table that's approximately 12 foot by 16 foot. We have 3 integrated robotic cells. These are KUKA KR480 MT robots. Integrated rotary tables that have a capacity of up to 50 tons. This one that you see in the picture is our newest machine, Clementine, and she's sitting on a really nice linear track from Goodell. We're really happy with this new integration. It's given us a lot of new flexibility for large work envelopes. We also have some aerospace capabilities in-house. This is one of our most precise CNC machines made by Northwood. And this machine, we are making some really incredible works of fine art and really sculpting stone to sub-millimeter precision at this point, which is a really exciting territory for us to study, and we'll talk more about that today. The other thing that makes us really unique as a producer is our ability to do all of our traditional handcraft and handwork in-house. So this is a image of a work by Ann Hamilton, an American artist, a recent gallery piece that we did at Stephen Hall's Gallery in Rhinebeck, New York. Some photos of that. And then some images of some of our master stone carvers. Almost everything that we make here with a CNC machine gets touched by hand. And you'll see that in the preceding slides. Here's Martin Foote doing some hand carving. Another thing that's really important about us is our material handling capabilities. We're set up to lift and handle blocks of stone up to 100,000 pounds, 50 tons. Which, in the image there, you see one of the blocks there is 80,000 pounds. The other one's just over our limit, 102,000. Incredibly large blocks of stone get brought in here on a regular basis. And, you might ask, why do you need 100,000 pounds of stone? This is a picture of a new work that I can't talk about who it is or where it's going, but it will come out into the world soon. Just an idea of what gets made out of a 100,000 pound block. We also have a division in Italy called Quarra Italia. We recently had a merger with Cervietti Studios and Martin Foote. Cervietti is one of the most historic old world carving studios in Pietrasanta, Italy. We've amassed one of the largest collection of historic plaster, and this is all about hand carving and is now a new extension of our existing hand carving team. So we're working both in Italy and in the United States. And this is just an example of some of Martin Foote's work. Who's one of our best collaborators. A little bit about the material that we use every day. As I said before, everything that we manufacture comes from a quarry, and we're very involved in the quarrying process. In the image on the screen, this is the granite quarries in Barrie, Vermont. We source all the material from quarries directly and in the form of block. We're deeply involved in this process. We work and partner with professional geologists to understand the raw material from the source. And we work very closely with our quarry partners through the quarrying process to extract the blocks specifically to the work that we do every day. Just a few images. This is the ledge at the Vermont quarry where we recently extracted the largest blocks of Vermont marble to be mined in Vermont in the last century. They were extracted from this wall on the outside. This is called the Maple Quarry at Vermont. And you'll see what those got turned into a little later on. A photo of the map of the quarry. We have a significant, process that we keep track of where materials come from and keep track of where blocks are extracted in the quarries. So the maps of the quarries that we work in can be really important. And then just some images, some other quarries around the world that we work with. Another thing that's really key to our work is how do we get it here? This is one of the procurement processes that we did a couple years ago during COVID. We learned, actually, we didn't mean to learn this, but we learned that it was actually cheaper to rent a ship to move this many blocks, and it's approximately 1,500 metric tons of blocks. It's actually cheaper to rent a ship from Antwerp and have it sail to the port of Milwaukee full of blocks than it is to put each block in an individual container. So that's some new territory that we've been exploring for how do we get our raw material. And yeah, I think you'll see more through the presentation of where the material comes from and what it gets converted to. All right, I'm going to flip it over to Leighton here. He's going to talk about one of our most recent works in New York City.
All right. I'm going to try and go a little bit quick here, but I am Leighton. This project is called Parallel Nature. It's the art wall that is at the base of the JPMC Tower at 270 Park Avenue. The four things that I kind of want to touch on here are the material sourcing for this project, the design process that went into it, the structural steel system that's supporting it, and then the install strategy that was used. And in the material sourcing for this project, we had some unique issues where we had budgetary constraints and then also material constraints where we were trying to find a material that fit Manhattan schist in some of the visual qualities, but the structural qualities of schist is that it would not be it wouldn't work well for this kind of application. So the stone that ended up being chosen is berry gray, which is a granite. And the section of the quarry that we ended up using was around this one here. They had this diagonal rift that's going through the quarry. You can kind of see it on the left-hand side of this image. And that led to a lot of triangular blocks, a lot of offcuts from larger blocks. And we ended up going through this quarry, measuring individual offcuts of mostly scrap material, and then matching pieces directly to their blocks during that process. So it was a really hands-on process of finding the home for each individual piece as we were selecting each block by hand. And the way that that was brought to it was in the design process. So these are the two scans for the two walls. They're derived from a surface scan of Manhattan schist that's located in Central Park. And all of the divisions for the walls is derived based on the texture of that mesh. So we collaborated directly with the artist on this project and divided up both walls to match the texture and then matched all of those pieces to blocks. And then you can kind of get a look at some of that structural system that's behind holding up every single piece. And this system is pretty unique in that it's designed to be a really, really quick install system and no adjustment in the stone placement. So that way installer isn't moving pieces around during the install, pushing out the next piece. So everything is located to one location, which is pretty, yeah, within a 16th of an inch. And it's kind of a natural for a stone project to function that way. Every stone has its own unique 3 points of contact to the steel ladder frame behind. 2 points are taking the gravity load. One of them is taking the moment load. And since every single outline of stone is unique, every single triangle of support is also unique. And kind of proving out that system, we did a 7-piece mock-up, which the thing that's unique about this mock-up is that those 7 pieces were not just discarded after the mock-up was completed, they were actually installed and used on the final project. So there wasn't any waste in the mock-up. They were reused. And it also kind of informed the design process of the artist in getting the final finish of the stones. We ended up having this system where we would dry lay large sections of stones all together and have them hand worked all at once so that you have features that travel across a lot larger regions of the wall instead of having kind of pocketed moments of texture. And this is just some of the scanning and the verification of that steel ladder frame system. It was really important that every single ladder point where the pieces were going to have contact was in the exact right location before it got to site. So this is some of that information of scanning every piece and then matching it up within millimeter precision. And this is the ladder frames going up on site. They're being attached there, and then these are the pieces getting dropped into place. And the install on this project was about 3 months long. It was projected to be about 4 months. The first wall is the south wall here, and it took just under 2 months. And then the north wall actually took less than 1 month to install. And the interesting thing about that is that there's less pieces on the south wall and there's more pieces on the north wall. So once they got through the learning curve of understanding the system, they were able to move at a really fast pace. We were installing stones at the height of this project. It was about 20 or 22 stones in a day when they were hitting their peak. So that is parallel nature. I'm going to pass it off to Pam.
This is Pam. And then this is City Jeff. And then City Jeff was a fine art commission, a massive marble sculpture, which is 7 feet tall and 3.5 feet wide and deep. And the artist gave us a fascinating challenge, which is the intended for the sculpture is to leave the machine marks as a stroke on the canvas to leave it as a final texture on the piece, so that we face like a huge challenge is how we handling this big piece and how do we make sure that the alignment and accuracy meets artist's requirements. So next we had to decide like how we gonna fabricate this piece in order to have like a parting line, because we know it has to flip at least once, and then instead of like splitting in the center, we're trying to follow the nature of the sculpture and then kind of like reduce all the undercuts as much as possible, so that result us has a face down position and face up position. And then in multi-axis machining, this is kind of like demonstrate how we use drive surface to control the tool angle precisionally, like how we kind of like using the we smooth the surface angle to make sure that the machine will travel accordingly to make the smooth connection between zones. Because in tool pathing this size of piece, we have to zone in like the head or the abdomen, the legs separately, and then this drive orientation will just help us like make sure the configuration of the machine is precisely controlled. And then the process photo is kind of like showing you how tightly that we control the robot into machining the sculpture. Like the top 3 images is kind of like the consistency images from a video. It shows like the tool head is really close to the head, and then how we machine the abdominal area.
Now we have to trust our software.
Yeah. And after, since we know that we needed at least 1 flip to finish machining, safety and planning moving was critical. So we normally do like digitally to plan the rigging and the moving in the sculpture. The step 1 and 2 is kind of like using the posi turner to rotate the piece carefully above the safety cushion, and then the step 3 and 4 is kind of like reconfigure the straps to lift it up and then just place on the machining jig for the next operation. And then this is kind of like the process photo of how we control the rigging process. And then after moving that, the problem is how do we reference the piece into a new position in space. so that before and after flip, we use kind of like we machine recess features into the rest of the blocks that allowed us to use laser tracker to take points before and after. Then that gives us the data before, the data of the spatial data that we can reference before and after. So this is kind of like how after we flip, we use the data to align, and then the fine adjustment is needed to make sure the model is correctly alignment. And then so we do a little bit grasshopper script to just kind of like fine tune the points alignment. Then that like a fine adjustment allowed us to make the average distance from the points itself from like 0.5 to 0.15 millimeter, which is like a 62% reduction of the error. And then after the machining is done, the next part is how do we configure the statue to a final sitting position. When we designing a lifting fixture for this, we kind of like simplify the geometry into just a sphere for the center of mass for lifting. And then when we engineer like the stone about like how we lifting in 3 points, the interesting part is like the neck itself can hold its own weight, but for safety, we just have the three straps to hold it. And then we use the inline scale on each point to just monitoring how close, make sure that all the straps has the target weight so that it doesn't like concentrate the weight into one local area. When the marble is when 2 marble pieces are combined, then we use like a big giant stainless steel clamp to hold 2 of them to move the piece around, and then that so this is how we like lift 2 pieces up and then drop into the final location. The stainless steel has its own lifting hook areas so that it just like clamp it, move it up, and then disassemble it so the piece is in the location. And then this is how Jeff is presented in the gallery in France.
So just a quick word on that. That piece within the Bourse de Commerce gallery, it's part of the Pinot collection, permanent collection in France. It's pretty interesting. One of the first times that we shipped our work across the world a couple of years back. So the next project I'll quickly present is called the 2-horse relief. This is 10-foot by 15-foot relief in Virginia Mist granite. This is on permanent display at the Met in New York City on the 2nd floor in the contemporary wing. So, 10-foot by 15-foot by 1 foot thick for a piece of granite by contemporary standards is it's really big. So one of the first problems that we had to tackle was, where do we get a piece of granite that big that's not only big enough to achieve the geometry, but has enough structural stability of its own to achieve the desired thickness of the bas-relief itself? We are only aware of very few quarries in the world that can make a piece of stone this big, and we ended up working with Virginia Mist Granite in Rapidan, Virginia, which is a very large formation of granite, which is in the Appalachian Mountains, and it stretches from Virginia all the way up through Pennsylvania. And it's a very robust and structurally durable granite.
It's the same stone as the Collier Memorial.
Yeah, thank you, Brian. Yeah, same stone that was used at the Sean Collier Memorial there at MIT's campus. So today, if you want to go see what Virginia Mist looks like, it's just down the way, and you can check out a memorial that we also fabricated. So logistically, getting a piece of granite that big, one problem right away is it has to have enough structural stability to survive the truck ride. So we had to order a block of granite that was 10-foot by 15-foot. Actually, excuse me, it was roughly 12-foot by 16-foot by 2-foot thick. It has to be thick enough to survive the impact loads of driving across the country on a semi-truck. So that block weighed about 80,000 pounds, and it was transported to Quarra on a 6-axle lowboy trailer. And you can see in the quarry, we really were pushing the envelope. This block at 80,000 pounds is significantly up to or over the capacity. So instead of using one end loader, they had to use 2 to get it on the truck. We had a similar problem here at Quarra. 80,000 pounds at the time this came in is quite a bit bigger than what we had worked before. So the first step was to split it in half. We rented a quarrying wire saw to split the block into two halves, roughly 40,000 pounds each. Logistically, 40,000 pounds has to be picked up and flipped over after the artist selected the side of the piece that they wanted to be the finished face. We had to do some work to get it flipped over. And so you can see the images here of us working with a VersaLift heavy lift forklift and an end loader to flip this 40,000 pounder over. Step one was to machine in some structural fixings in the back of the stone. These are dovetail cleats that were custom machined from stainless steel. It's a two-part assembly that when you insert this into the stone, it hooks into an undercut. There's no glue. This is entirely a friction fit connection and sort of an impossible assembly that once it's bolted together inside of the cavity that we machine in the stone, it cannot come back out, not without a tremendous amount of force. So once we got the backside machined, we had to flip it back over and start working on the front. This is where we ran into another small problem. We did not at the time have a CNC machine big enough to house this big of a piece of granite to carve this geometry. So we had to work the finished bas-relief surface in two halves, one half in the CNC machine, the other half sticking out onto the factory floor. This involved some significant processes internally to realign the part and adjust and register it once we had flipped it for machining. So upon completion of machining, you can kind of tell here in this image, around the perimeters, the design thickness is 4 inches. And at the withers of the horse, it gets to approximately 12 inches. This becomes a new significant problem in material handling because we have to lift the piece up without breaking it in half under its own self-mass. So you can see in this image here, we engineered a large spreader frame, tubular spreader frame that we bolted together, and then we installed a set of I-beams underneath the piece at roughly quarter points to allow us to pick the piece up carefully and stably and transport it across the shop floor. And the next step was to affix the artwork to a custom stainless steel frame, which acts as a carrier and a structural stiffener for the bas-relief artwork for future purposes. This piece of stainless steel is designed and engineered at the lifespan of forever. The intent of the artist is for this work to not leave this planet, and it's actually pretty wonderful that it got housed at the Met. So you can see in the back side of the piece, the dovetail pocket are filled with the structural fixings, and then you have a large stainless steel frame stiffener. The final finish of the piece was a sandblast finish, and this is a good image to kind of give you a sense of the scale of the artwork hanging in our factory from the gantry cranes. And then we washed it up. And the next step, this is where things got a little bit dicey because we have a piece of work that has been now accepted by the artist, and its value in the art marketplace is significant. I don't know what the value is, but more than is an average day at work. And so we had to then load this piece of artwork onto this custom engineered crawler frame. You can see on the right side of the image where it was bolted to the frame. That frame, and this is a good visual of how we mounted that to the frame. So we hovered it over the frame, slid the two together, made a series of bolted connections, and then relieved the crane pressure and transferred the load onto the crawler. That's seen here in this image. That crawler is custom designed to roll across a shop floor or a museum space. And another nice little feature of it is that it just barely fits inside of a high bay shipping container, like with literally half an inch to spare or less, that was kind of a interesting moment for us, stuffing that in a container. As you can see here, there's Mark and Phil, two of the handlers of the work. They had a long day along with me getting that into the container. Then we loaded it onto a semi truck and said goodbye. Here's just a couple images. One of the things that we encountered during machining that I wanted to point out here is you see those vertical banding lines. We found that the PCD tooling that we were using leaves a slightly different color signature in the granite during machining. There's no geometric difference, but it's a different color. And so that was one of the things that prompted us to sandblast the piece. And then an image of it hanging on the wall at the Met. If you go and visit this piece, it sort of just looks like it's hanging on the drywall, but all of the armature that you saw on the factory floor is buried in the wall at the Met in perpetuity. So that's the two-horse relief with Charles Ray. I'll give it to Brian to intro the UVA.
So this is a project we did a few years back with Heller and Yoon. This is the UVA Memorial. It consists of a ring of stone that matches the diameter of the rotunda on the campus there. One of the big design challenges through this, we worked through quite a few rounds of mock-ups, both digital and physical mock-ups. The artist that we were working with on the project wanted to have the eyes. You can very faintly see it here. You'll be able to see it in some later photos, but eyes of one of the slaves, or the first known slave, what was her name? Isabella Gibbons. So this was a memorial to enslaved laborers, and it was meant to honor and kind of put those people's names in something more permanent in this memorial. So as part of those mock-ups, we went through a lot of different studies of photo V-carve process. So traditionally photo V-carve, I don't know if you guys are familiar, but that's basically using a black and white image to create a depth map. It's typically done on a flat surface, but on this one, they had both a scalped texture that was supposed to be reminiscent of the slaves' scarring that they would have on their back. And then also they wanted to have the eye pattern as well in that same surface. And the whole outer shape is this kind of tapered conical shape. So we had to take the method of doing V-carve on a flat and find a way to map it parametrically onto this complex surface and still achieve the visual effect. So we have some photos later on that show some more of that mock-up process, but the fabrication for this project, we had to distribute across multiple machines. We had a range of pieces that went from very large volumetric pieces, and those were done on some of our larger robotic cells just because of the work envelope, as well as some of our other CNCs for some of the flatter panels that had the texturing, as well as a water feature that was in the center. All of the machining on this project was done with blades. That's a pretty traditional workflow that we use. We use blades horizontally to do finishing in granites because it's a harder stone. You need that stronger tooling. It also is a huge time savings versus using traditional milling tools. Again, this is also another project done in that same Virginia Mist stone that the Collier Memorial's in. Just some photos of our mock-up pieces. Here was a dry lay that we did. So we had spent probably a couple months working with the artist and the architect developing a digital version of this where the eyes looked like they worked. The difficult thing with that, obviously, that's a digital environment, so you don't know for sure that it's going to work. And so ultimately, when we laid everything out, it was really rewarding to see that all the studies we had done, both in this and some mock-ups, actually did result in being able to see the eyes in varying light. We also performed, I think this was a 7-piece mock-up for the architect, just so they could get a sense of scale, ensure that the way that they have their design laid out was going to match what they wanted the experience of it to be. So the interior section is meant to kind of be this contemplative space. You can sit on the bench and have time with all the names and the markings that are on that inner wall. So this was a way for them to verify their assumptions about the scale of everything and the geometries. Again, these are just some of our full-scale mock-ups looking at different depths of V-carve, different spacings, and studying how that was actually going to work out in the end. And then Alex will talk some about the installation because we also performed the installation on this.
Yeah, so one thing that we experienced here that hadn't come for Quarra in the past was to do a large-scale installation. In my experience prior to joining Quarra, I had done 4 or 5 public art installations. Nothing near as complex or as significant as this one. But I, worked alongside Brian. Brian and I developed a lot of novel strategies for install, and then I went out there and ran a crew on site for 4 months installing the memorial with our own team. It was a unique install because we staffed it with our own people, and some of the people that I had on site, shoulder to shoulder with me, were master stone carvers, hand workers, masons, people that have really old world experience in making things out of stone. So one of the things that we contributed to the project, we did all of the engineering, structural engineering for retaining the pieces to the slab. You can see we didn't do the foundation, but attached to the foundation is a ribbon of stainless steel That ribbon of stainless steel was very precisely located, anchoring that tied each of the back sides of the stone for vertical uplift, negative uplift of the panels, and also retained them from tipping over. Just a few images of the interior wall of the memorial. We set all of the stone on site with a 15,000 pound capacity lull. The site conditions on this site really weren't conducive to using a crane. The other thing that we know from our own practices here at Quarra, picking up fragile stone and having to do precise setting with a crane with a 100+ foot whip line is frankly very difficult to do and risks the piece a lot. And so we opted to use a much more controlled piece of machinery where we could really go slow. Stone is slow as a material, and I think installing it is going slower is better. Just a few more images of the install. There's one of our carvers, Eric, doing some final dressing to a piece of stone on site. And then an image of the eyes emergent from the backside of the piece. This was a really special moment for us on site because it wasn't until we had all of the back wall pieces on the memorial and in the right sunlight that we got to see if the eyes actually worked.
One thing that is interesting with this too, in different sunlight, the eyes entirely disappear and what you see are the scallops. So it has a really nice play between those two textures.
Another image just giving a sense of scale and the way that the inner wall and the outer wall meet each other. There's a transition point where it goes from architectural panels that are about 6 inches thick to full-scale solid thickness pieces of stone. If you happen to ever be at UVA in Charlottesville, definitely go and check it out. It's a really inviting space. Just a few more images of it as built. All right, flipping back to Brian, another one.
So another round of, we've actually done 3 projects with this artist. So Sarah Z is a media artist, and she has a series of boulders. The primary concept behind it is that as if you found a geode, split it open, and instead of the crystals inside, there's a pixelated image. The interesting thing with this project is probably to date, it served as our biggest kind of R&D development over multiple versions of the same thing. So we've done three sets of these boulders, one in San Francisco, one in New York, and one in Santa Monica. The kind of wild thing with these is they consisted of between 180,000 and 360,000 tiny holes that we then custom mix up to 126 different colors with natural earth pigments and then extrude those in the holes. So it's effectively like the world's worst color by number. And when we first started doing this initially, the biggest challenge with it was in the color mixing. And the first time we went through that, we got a couple of our hand workers who had a little bit of an artistic sense for color and basically was working through a process of trial and error. So in doing that, we were able to hit maybe like 60% of the colors pretty quickly, but then the last bit, it was a lot of trial and error. And I think ultimately we probably mixed about 1,000 different color recipes to try and hit the 126 to get approved by the artist. When we got to round 2 of this project, we decided we did not want to go down that route again. So we worked with an artist from the University of Madison here in town. She's kind of from their group. They classified her as like a color mixing and color theory expert. So we brought her in. She helped us with a lot of our initial recipes on the second version of this boulder. And then ultimately there was like the last maybe 10% of the colors that we still couldn't get. She was able to help us like mix in colors that we never would have thought to mix in. But again, this was a more or less process of trial and error with some guidance from an expert. The final version of this project, we wanted to get more technical, more scientific about it. Because one of the challenges we were presented with every time is we would get a color, we would mix it, we'd match it to the swatch and be like, hey, that's a match. And then the artist would say, no, I think it needs a little more red or a little more yellow. So as a way to kind of eliminate the subjectivity of it, we got a device which is a color photospectrometer, which is able to actually analyze the color spectrum of any given color. And this is typically used in the painting industry. So with that, we were able to scan our swatches, scan a bunch of base color pucks, And not only does this thing give us a kind of baseline recipe that kind of gets us to the 85% match starting out, it also lets us say this is the same color. Like there is no argument. You can't say it's a different color. This is the same color. So this was a really interesting process that we went through and drastically cut down the time. I think on the last one we were able to get all 100, I think it was 107 colors approved within a month, whereas on the first round it took us probably 4 months of back and forth with the artist.
And that software gets smarter the more colors you measure and the more pigments you mix.
Yeah, it builds up a library. So as we continue to do more of these
colors.
projects, we're able to kind of have a library we can draw on.
And it's sort of a recursive exercise. You get closer and closer to target.
The next part of this project that we kind of went through another R&D development stage was the fabrication of it. So on the initial boulder, the request was, hey, let's go find a boulder at the quarry, cut it in half, and then do all the painting. We did go through that process. The challenge with that initially is it's very hard to find a boulder of the size and geometry that the artist wanted. We did find one, went through the whole process, and then ultimately the geometry of the backside didn't have enough character, it didn't have enough features to it. So you can see in this picture here, we then, after the project was almost completed, had to go and by hand reshape the whole back. After that, for round 2 and 3, we just collectively decided it was better to start from a block of material and then basically machine a boulder to some geometry that the artist has designed, and then through a bunch of handworking and machining processes, bring back some texture and make it look more natural. It does feel a little bit backwards doing that, where we're taking a block and making it look like a boulder, but in this case it gave us the control and it gave the artist the ability to have the size that they wanted, because before it was all constrained on how big of a boulder you could find.
It was easier to machine a boulder.
Yeah, it's easier to machine a boulder for us than it is to try and find a boulder. The other thing too, we kind of went through a few different rounds of process for how we actually fabricate them. But ultimately what we've landed on, we start with a block, do some wire saw cutting, and then with blades again, machine the base geometry. And then where we have kind of deeper areas, we'll go in with a milling tool. And then the final, like turning it back into a boulder, is all done by hand, using some of our master carvers to bring some of that texture back. Another significant area that has been challenging throughout this whole process is how we apply all these tiny, tiny holes across the face. So far, what we've been doing is we've been sandblasting these holes. Initially, we machined the sandblasting template on one of our CNCs. The first boulder was able to fit within a 4x8 sheet, so that wasn't too much of an issue. Second boulder, you can see here, was much larger, so we couldn't fit it within a single sheet. So we had to find another way to do that. So we ended up finding a laser cutter who could cut it for us. One of the challenges that we came across with that is, how do you align 2 of these templates to ensure that everything has the perfect spacing and you're not going to see a shift, and then also deal with some tolerances of their laser cutter to where you would get some slight shifts in the grid. For our next iteration of this, we plan to actually machine these holes on one of our CNCs directly into the stone, as a way to kind of eliminate one of these variables that gave us some difficulties in the process. Another interesting part of this that we've kind of grown as we went through the project was the handworking process. So because we're working with epoxies, we're working with so many different colors, they have shelf life, they have cure time. Once we get everything extruded in the holes, we then have to go in and handwork it down and then go inspect all the holes to find anywhere where there are potentially bubbles or holes maybe that didn't get filled properly. So the first version, I don't remember what the exact number was, but there was a very large percentage of holes that we either had to drill out and refill or just touch up. By the time we got to the last version, our fabrication processes had improved to a point that we didn't have to do that on nearly as many. Probably the largest area of development on this project has been in how we extruded the colors. For our first boulder, we used an overhead projector, aligned it to the grid, and as you can see here, basically lit up the holes that we wanted for each color. And then, amazingly enough, we had a group of 4 people that we would get from the art school, and they would come and just, they would paint this by hand with syringes. This process obviously is very, very labor intensive. It was prone to some errors because you have the tolerance of a human picking which holes to put it in, maybe not always following the projection. The projection doesn't necessarily always line up perfectly with our grid. So the other thing too, we had, because you're working with these epoxies, there's a lot of proper procedures that when you have this many people working, not everyone was following. So people were getting allergic reactions to the epoxy. There was a lot involved with having people hand paint this. So the second round, we decided to switch up the process and make it more automated. So we used a robot, designed a custom end effector to go on the robot. And basically with this setup, rather than having 4 people working for 4 months, we could have one person being able to extrude up to 10,000 holes a day, which helped basically eliminate people from getting allergic reactions because it was a much more controlled environment. And also let us get the extrusion done a lot faster and a lot more accurately. And this is the result of the one that we did on the robot after it was all honed up. For the third iteration, one of the challenges we had was the fact that, okay, a robot's great, but you have to bring the piece to the robot. And as you can see in that last picture, it's really tight in here. And we had some challenges reaching some of these extents. So we had to like very carefully position the boulders to be able to do that and then align to the grid. The next iteration, we purchased and built a gantry that, as you can see, is portable. So we can actually move this over top of a boulder. So we can have the boulder set up wherever we want. The other challenge we ran into is the temperature control of your environment is really critical, and the humidity. So with this, we could move it where we needed to and ensure that we had good controls so that our extrusions would be better. We would have better curing of the epoxy and would have less issues. And just some process photos. So these are the end results of those boulders. This is the one that's in San Francisco. This one had 240,000 holes between the boulder and the paver. One other interesting thing too is these surrounding pavers are all concrete pavers, and they wanted the stone to mimic that pattern. So what we ultimately did was we fabricated this out of one single slab and then cut it up into the pavers so that they could then be set and have similar jointing. The second round, I believe, is at a residence in New York. But in this one, it was just 2 boulders out in a field. And then the last iteration was the most holes. That had 360,000 holes. And this is in Santa Monica. One interesting thing that came out of this project was a desire internally to kind of further explore painting in stone and what we could do with dots and colored dots in stone. So these were some studies that our QLab team did, just looking at different surface textures and putting holes into that, coloring it, as well as doing, I think this was one that actually Sam did, which was a pixelated image of an eye based on the depth and the size of the opening. So that was just some interesting work that came out of this whole project.
So, and then we'll just briefly run through this project. This is the Emmanuel Nye Memorial. This is the last thing we'll show. It's a work in process. This is not built yet. This is a memorial in Charleston, South Carolina, designed by Michael Arad to commemorate the parishioners who lost their lives in the tragedy at the church in Charleston. So here's an image of the memorial walls rendered. This is made out of Vermont Danby marble. This is the project that I was saying earlier on, that we extracted some of the largest blocks that have been transported out of Vermont in the last century. These are very large and complex pieces of marble, and it also has a fairly unique structural system. Each of these, there's very few structural pins in each of these 2 bench walls, and they support one another through their own geometry. Which you can kind of see in this image here. It's a bit hard to explain without looking at the engineering drawings, but each of those sort of undercut wings, each of those pieces of marble underhook one another, and as the structure gets built out, they act on one another in kind of structural unison. Maybe I'll switch to Brian real quick to talk about this. So, or Sam, yeah. So the machining process. This project, I'll just intro by saying, the tolerance requirements on this project are the most stringent thing that we've ever seen, both in fabrication and in installation. We're talking about sub-millimeter precision for the structural surfaces. And in addition, the pieces in the field have to be placed with sub-millimeter precision. So Sam will talk about the machining, and then we'll try to take a stab at talking about the install. Go ahead, Sam.
Yeah, the process is kind of like showing like each of the steps. It's kind of like a crossing in the whole machine. It's not just the piece can be done in one go. So it requires to have the reference cut to have a register point, and then cut out of the couple surfaces out of the one position, and then requires a flip afterwards, and then finish all sides. And then so that's kind of like how we decide to choose how do we utilize this as using the repetitivity of the CNC instead of chasing absolute accuracy in the process. So if we trying to achieve like absolute accuracy across all machines, that requires us to tie down all the machining handling setups and then all the reference points that we make. But if we use the repeatability and then use that to generate another surface to correct it, it kind of like skip the process of chasing the absolute accuracy, but we can still achieve the accuracy in the stone. And then how we do it is we capture the data from the offset machining scan, and then we use that data to make a deviation map, and then reverse that map to create a compensating surface to do a final pass with the machine. And then for piece handling is like the finished piece, or the piece is kind of like a curvature, and then it's extremely dangerous to handle like a tall, thin, and curvature piece. So to handle this kind of like a geometry, we built like a custom cage to kind of like holding it down tight, and then so that allows us to pick it up slowly and then rotate it and then stand it up, and then kind of like face it down in a slow motion with a crane.
So just speaking a little bit to close this one about the installation, we're underway on this installation right now, but just an image there to see. Before the pieces get shipped to the field, there's a lot of investigation about ensuring that the pieces have the appropriate machining tolerance, and then we also lay them out in the shop floor. So this is a dry lay of 8 of the pieces for one of the 2 walls in the courtyard. 3D scanning is a very significant part of this process. As Sam was saying, everything is 3D scanned, best fit compared to the 3D model to ensure that our precisions, especially along the structural surfaces, are adequate. Another point of note, all of the structural anchorages on this project, because of their custom nature, were tested in a testing facility in Northbrook, Illinois with West Cheney and Elsner to determine their individual structural capacities in this specific material. You can see on the surface of those stones, there's all these lines where a geologist marked out any linear features in the stone. So after doing this break test in the laboratory, which I went down and I worked extensively with them on this testing program, and I went down and observed the testing. But this was really just to keep track of the breaks and see how corollary they are to the grain direction of the material, effectively, the rift, you might call it. In the process of this project, we've developed what we think is a novel undercut anchor assembly. So this is the structural anchors that's anchor this into the marble into the slab. What we do is we mill a 3-inch diameter hole with a core drill, and then we have a very long tool that we stick down in that hole to make a belled undercut shape. And then we use just a hydraulic grout product from Sika to bond the double nut washer assembly in. And this anchor assembly really outperforms most mechanical undercut assemblies. In addition, it kind of blew epoxy out of the water in the laboratory. So just a little point of note there. We've developed our own installation system on site. It started a few years back when we installed a memorial on site. So that's an aerial view of the site. And that's actually, I think that's me actually on site. We all of us were not just in the office. We're on the factory floor, and we go out and do this stuff in real life every day. So an image of our crane system that we developed on site. All these pieces, as I was saying before, have to be set to sub-millimeter precisions in the field from a structural point of view to ensure that the structure is adequate and can be relied upon. So an image of our gantry crane system that we engineered and built. This is our crew down in South Carolina installing, and then some photos of the marble pieces being laid out on site. The site is very tight, so we built this train track system where we put 15,000-pound pieces of marble on a cart, and then we roll them out into the memorial courtyard, where we rig them up with a crane and transit them across the site. And then, briefly, this would be a little bit hard to understand, but what you're looking at here is we have taken all of the three-dimensional scans post machining, and we've realigned them with the original design model through best fit algorithms. And then on the face of each piece of marble in the field, we have a physical registration point that we've tracked through scanning. You can see those nodes on the screen there. So when we go and set these pieces in the field, the setting parameter in the field, we use a laser tracking system with a handheld probe. You can see Brian there using the handheld probe on site. So when we set those stones down, we have our laser tracker oriented to the world, which is the exact world that the model is positioned in the Rhino model. And then we go set the piece of stone down in the field. We use our Leica laser probe, which is accurate at 20 microns over 400 feet for a laser shot. It's super accurate, and this is kind of insane, but we've been setting stone. I think our tolerances right now, we're in the hundreds of millimeters, but on average, we're 0.1 or 2.2 millimeters from the design position with this methodology. So we're getting a little bit better at structural and performative setting here at Quarra, and just an image. And then I'll close with this. It's a little thing that I wrote just to kind of summarize. Often when we begin a project in stone, the solution is unclear, sometimes seemingly impossible. Our work is driven by design intent and artist vision, grounded in engineering and material science, and realized through skill, precision, and generations of stone fabrication experience. There's no manual for what we do. Every success is built on a foundation of failure, and failure itself is essential. Our willingness to fail defines our ability to push the limits of practicality. Failure is a mechanism that expands the boundary of what's possible. We work iteratively using digital space to simulate reality, to solve for the unknown and test variables through analysis. Digital tools let us refine the boundaries of traditional stone fabrication, pairing advanced metrology and robotic precision with old world craftsmanship. But every assumption must still be proven in reality, on the factory floor, full scale, in the actual material. The result is binary. It either works or it doesn't. Stone, like any material, has limits that govern its transformation from solid earth into architecture or sculpture. Knowing those limits requires total commitment to the material and a relentless curiosity about its geology and mechanical behavior. What has been done before is simply a reference point. Discovery lies beyond. For all of us as makers, designers, engineers, architects, and artists, the essential question remains: how will we build it? The answer begins as an idea, a drawing, a model, a provocation, and is often proven through making, testing, and refinement. In the end, every idea must meet reality in material form. That's where thought meets hand and where the spirit of Mens et Manus truly endures. Thank you. Appreciate it.
Thank you for the very generous presentation. Due to time constraints, we can take like 2 or 3 questions?
Yeah, sorry, we went a little long.
Yeah, no worries. That was great.
We have a lot of stuff.
We amassed a collection of over 5,000 photos in the buildup of this presentation. So we appreciate you letting us share a couple hundred of them.
No, thank you for sharing everything. Sorry, go ahead.
Yeah, thank you for your presentation. I'm just curious, when a designer or architect comes to you with an idea, it's clear the only difference between it existing as a Rhino model or a napkin sketch and a real project is your knowledge and knowledge of the material and of the fabrication technique. So does it ever sting that the designers get most of the credit for the finished projects?
That's a great question.
You get used to that.
Yeah, I'll try my answer. I'll let the guys answer too. My answer has morphed over the years. I think when I started here 10 years ago, actually in some ways even with the Memorial to Enslaved Laborers at UVA, there wasn't very much mention of our company. There was a little bit. We got a little bit of credibility, but it stung a little bit to your point. But as I've gone forward in my experience with stone, I've found that what we do every day in realizing these works is not different than what history has suggested. Even carvers like Bernini, they had dark horses that did their work. They had people behind the scenes that could carve. I mean, there's a known carver behind Bernini. I'm sorry, I don't know his name, but that was a better carver than Bernini. And Bernini gets all the cred, and but I think I've come to actually sort of enjoy um, being in this role of making the work, and in some ways not being known for it. It's okay in a way.
I think the interesting thing for me too is just knowing like one that some of these things are going to be around for a long time after we're here. I think it's just, at least for me, it's really fascinating to be part of that and be able to contribute to that, whether or not we get credit for it. But also in a lot of these, because especially with some of the memorials that we're doing, um, it and for us, it's not really about us; it's about what the memorial is supposed to be representing. So in those senses, it's more just that we're helping to bring some of these memorials honoring these pretty important things to light. So I think that makes it, again, initially it is a little hard to not get the credit for it, but in the end, I think those other things outweigh that and are kind of, at least for me, they're more critical and more important. I don't know if you guys have any other.
You guys got anything to add, Sam or Leighton?
I think for some of the project, like architectural wise, it's like the making is kind of the most important part. But for fine art, it's kind of we're representing the the geometry in different materials. So if the artists already have done that in other things, and then I think we're just kind of specialize in stone to help them solve the problems.
Mm-hmm.
Yeah.
Yeah, I think that everyone else has probably summarized it well. I think that if you would ask me right when I started, that I'd have a different answer as well. But yeah, I think that there's a point where you begin to understand that this isn't necessarily like a new practice. This isn't something that is just like a modern thing that has been happening. It's something that's happened throughout time. So, and I think it will continue to happen.
Yeah. First of all, thank you so much. This was an incredible presentation. Lots of wonderful work. I guess trying to contextualize this, like stone machining and stone fabrication, let's say at the building scale, do you see a future where stone will find itself again playing a more significant role in how we make buildings, specifically how we structure them? And I ask that because, I feel as though the way we build buildings today, it's becoming increasingly more tectonic. Things are generally made for the purpose of being installed rather than crafted. And while what you're making, I'm just like trying to think, even though you're making a lot of these amazing sculptures to be installed, you are ultimately also crafting it. So I'm wondering, do you find that craft returning and being reintroduced at the scale of the building?
I've often, since I started working here at Quarra, I was very struck in the beginning by how much stone goes into the world as a 1 inch thick veneer. And through my time making 1 inch thick veneer and sending it to job sites, I found that it's actually a really poor choice for a building. And in so many ways, I think we should re-engage masonry as a construction system. I personally think we should be building with large chunks of stone. As I said in my preface, it's the most abundant material on the planet. It's right beneath our feet everywhere we are. And in some ways, it could be one of the most local. So for me, I hope, and I want to contribute to it, a future where we start to use stone in a tectonic way in buildings. I think there's a big push right now for mass timber. I don't see any reason, why, when used correctly, stone can't be deployed in a mass stone sort of way, you might say.
Well, our presentation obviously focuses more on some of the more fine art and like pavilion type works, but we do have a good bit of work, especially within the last 5 years, that's going more towards bigger, more monolithic pieces of stone. The stone serving as its own structure, so more gravity bearing rather than just simply clad.
Yeah.
Even right now, we're looking at 2 or 3 projects that are looking at some massive pieces of stone. Some of them, one of them is actually looking at post-tension stone as a structural element. So I do think there is kind of this push we've seen in the last probably 5 years. And some of that might just be in more how our work is getting out into the world. People are starting to see that, oh, wait, we can do some of these things in stone. But I think it's also people are wanting to go back to some of those longer term materials, more performative materials. And also people are starting to come to realization too that stone also is a lower carbon footprint. It's actually better in terms of waste. So there's a lot of things that are making people turn back to stone.
Yeah, the other thing I would say too that I think is really essential is that we need to be, as architects, engineers, whatever, we need to be designing the details that allow this work to come into the world.
Yeah.
And one place that I'm personally very fascinated by is the geology of stone. What is it? How strong is it? And then going into the structural laboratories and breaking it and learning about what are its capacities, how reliable is it, what's the variability of the material, and can you genuinely engineer to it from a structural performance point of view, and rely on it in that way. And I think that type of work and research isn't happening, in my opinion, very much in stone as a material. There's a ton of research right now that's gone into how do you make super thin, lightweight cladding systems, and they're so non-durable. I think everybody's going to be kind of disappointed in 25 years.
Well, there's a reason why some of the oldest
know.
buildings that are still standing are almost entirely stone.
Yeah, and I'm also fascinated, I would say, by the archaic. I mean, you look at there's a stone I think in the West Wall. It's called the Jericho stone. It's a megalith. It was moved by humans a long time ago. I don't really know when, but I want to say it weighs something like 350 or 400,000 pounds, which is incredible. I mean, it's incredible. I mean, in the contemporary era, when we buy a block when we call a quarry and go like, hey, can we get a 100,000 pound block? They fall off their chair, and so I think, it takes us a little bit sort of through the lens of the work we just showed you, kind of pushing a new envelope in this material, finding ways to get bigger pieces, doing the structural analysis. And I think that's what helps it break through. And the other last thing I would say is I think architects, engineers, and us as makers need to work together more and earlier, because I think there are ways to solve through these challenges and bring this stuff into architectural form.
Yeah. Great. Thank you.
Any more questions?
No, good.
Do you want to just move over?
I'm Jim Larson. I'm a stoneworker myself, actually, here in New England, and I'm crashing this just for the information.
Oh, cool.
To chat with other stoneworkers and designers. From my perspective, as an artist carving stone, it's like the most humble material on earth. As you said, it's the most common.
Yeah.
And these projects that you showed are crazy. Some of the wildest, certainly some of the wildest projects happening in stone. And I guess as you manage budgets and as you manage timelines, you must constantly come up against this factor of technification or complexity, or like climbing the ladders of precision. And I'm wondering what some techniques that you have for managing that are. Like, how do you make stone more accessible for more people by keeping it humble and making things not so technified?
That's a great question. I think JP Morgan Chase, the first project, what is it? Parallel Nature is maybe a place that sort of starts. That's it's an architectural facade. Those pieces are really crazy. But from a machining point of view, we didn't talk much about the machining. I can tell you that the machining of that project was very simplified. We early on in the project identified that we couldn't just mill every piece on that job to this millimetric precision. And so we had to find a way with some very common practices in our manufacturing to generate that square footage and texture without it becoming so cost prohibitive that you couldn't build with it. And I think this is definitely a thing that we are confronted by. And I think the only way that we're able to advance that conversation is to keep doing these challenging works, because out of every one of these very challenging works, we often find something in our manufacturing process that it gets economized. One thing that we didn't talk much about, but it's on that frame, is block utilization. We used to do this the old way. We used to measure a block with a tape measure, and figure out how to nest all the parts into the block by hand. And we've let the digital tools bleed into that, where we can measure a block either by hand or take a quick 3D scan of it, and we can nest a project's parts into the block, and we can have a much higher utilization of the material, which has a really dramatic effect on how much raw material we need, which I think makes jobs more sustainable, but at the same time, more cost effective. So it's definitely a thing that we're confronted with all the time. And I can tell you, sometimes manufacturing complex works like this, we find out the hard way that we underbid it, or maybe we're not going to make as much money as we thought. But I think that as a company, we're sort of comfortable riding that line, because I think there will be benefits to it as we continue to move into this work.
Well, I think also these projects here obviously are some of the extremes. But one thing that we've been really growing in our team, we call it design assist. That's one that you probably find in a lot of places. But I think one of the primary goals of that is, both working with architects and artists, is finding ways to make stone, because everyone initially thinks stone is going to be more expensive, more complex, more difficult to fabricate. But through that design assist work, we're trying to get in early with different people and to kind of help educate and show, no, you can get stone with these creative methods and still maintain whatever budget you're trying to work with. So I think a lot of it's obviously not as complex as this, but there are definitely a lot of opportunities where we're using some of the things we learn through these more complex processes and factoring that into the large percentage of our company that actually still does more traditional flat work, simple stone.
Yeah.
So it is a good balance.
And I oversee our estimating largely here at Quarra, and I think along the lines of what Brian's talking about is that what we see is projects that come across our estimating desk when they're in late DDs or already gone all the way through CDs, they're often substantially more expensive than getting us involved early in the project, because we've learned so many of the lessons the hard way with stone for how it can be detailed and manufactured. And I think one of the things that we try to advocate for is to be brought in as a collaborator earlier on in the process, so that we can, serve in that capacity where we can make a project more doable, even a complex project. I actually think there's a future where really complex work, we can find a way to make it more cost effective by being involved in design earlier. And I think that's really for our team here at Quarra. Like, there's how many architects work here now? 10? I mean, we want to be part of the design process. And I think it's what drives us. And I think we want to be confronted with the question of like, okay, that thing's cool, it's crazy, how are we going to build it on budget? Because we want to make it. And I think that's a constraint that we work with literally every day here at Quarra.
All right. I think that's our time. Unless you have
No, I was going to say hi to Jay. Yes.
All right.
That's
Thanks.
awesome.
Thank you guys so much for the presentation.
And
Thank you.
if any other questions do come up, you can definitely send them to us.
Yeah, definitely send us an email. Thank you.
Thank you.